So in the third video of the trilogy, we are going to focus on prediction and interval estimation. That is, we could predict using our regression equation, we could get point estimates. So for example, what mark can somebody who studied for 25 hours expect to get? We get a single point estimate. But in much like what we did in chapter 8, chapter 9, where we wanted interval estimates, because point estimates tend not to be very reliable. So in that case, we would want an interval estimate. So that interval estimate, we have two types. One is we would like to have an interval estimate for the average mark of all the people who study for a given amount of time. So let's say the 25 hours. I'm sure if we were to look at the regression or the distribution, we will find that there are a whole bunch of people who study for 25 hours. So it kind of looks something like this. If this is our regression line, right? At each point on the line, at each point on that line, so this is one x value, let's call it x1, x2. Well, there's a distribution of values for each of those points. So there's a distribution of values. That distribution has a mean for that given x value. So there's a mean value of y for x2. And this here would be the mean value of y for x1. So we would like to actually come up with a confidence interval for that mean. Come up with a confidence interval for that mean. If we could do that, that might be useful to us. So the confidence interval is given by, if we want a confidence interval for the mean value of y at a given x, it would be y hat plus or minus t alpha over 2 degrees of freedom times the standard deviation of the errors times this term right here, 1 over n plus xg, the given value of x, minus x bar, the mean value of x, over ssx. So this is a 1 minus alpha times 100% confidence interval for the mean value of y at a given x. Let me write that down. It is a 1 minus alpha times 100% confidence interval for the mean value of y at a given x, which we will refer to as xg. All right? So xg is that given x. Cool. Now, we also would like to have what we call a prediction interval. So that's a confidence interval, but a prediction interval. So in this case, what we're saying is that we would like an interval estimate. When I say this case, meaning the one we just did. If we're trying to predict the mean value of y at a given x, then we're saying all at a given x value, say for example 25 hours of study, there's a whole bunch of students who will get different marks. So the average mark, right, is what we're interested in. Now there's a second interval which we call a prediction interval, which we could say, give me a confidence interval or prediction interval, just to differentiate the two, for the actual value of y at a given x. So we call it a prediction interval, the actual value of y. So what mark can I get if I study 25 hours? And can you give me an interval for that? That will actually be different from trying to get a confidence interval for the average value of y at a given x. The formulas actually look very similar. It would be like this. So a 1 minus alpha, or 1 minus alpha, times 100% prediction interval, we call that one, for a mean value of y, not a mean value, sorry, for an actual value of y at a given x, right? At a given x. And the formula looks something like this. Y hat, very similar to what we had before, plus or minus t alpha over 2 degrees of freedom, what we had before. SE, we also had that, but then we're going to multiply that by 1 plus 1 over n. So we've now added this term right here, plus xg minus x bar over SSX. All right, and that is the prediction interval. Cool? So one is predicting the average value of y, one is predicting the actual value of y. So now let's do a problem. So we're going to have hours. Somebody study for 25 hours, predict their mark for us. So if we're predicting that mark, we would have exam estimate is 39.40 plus 2.122 times 25. It turns out that that is 92.45%. That is what the person can expect to get. And that's just a point estimate. So we would like to do better than that by saying, let's translate that to an interval estimate. All right, interval. So here we go. First one we're going to do is get a confidence interval for the average exam mark for students who study for 25 hours. So find a 95% confidence interval for the mean mark of students who study for 25 hours. So we're just trying to find the average for those students. And so recall what the formula was. And so it would look like this. I'm not going to rewrite the formula. The formula is already given to you. So we will substitute in that formula. We will have 92.45, that's our 0.45, that's our point estimate, plus or minus the t value, t alpha over 2 degrees of freedom. Well, if we want a 95% confidence interval, alpha is 5%, alpha over 2 is 0.025, so that would actually give us t 0.025, we have 8 degrees of freedom. We already have this value is 2.306. So that is 2.306, that's our t value, times the standard deviation of the errors, which was 10.71, and then we want 1 over 10 plus xg, which is 25. Now we want x bar. What is x bar? Recall the sum of the x's was 188, so therefore 188 over 10 is x bar, which is 18.8 is x bar. So minus 18, 18.8 over SSX. Remember SSX was 297.6. When we work this out, we will actually get 92.45 plus or minus the margin of error, which turns out in this case to be 11.82. So according to this, the average value of y for students who study for 25 hours, so the mean value of y when x equal to 25 lies somewhere between 80.63%, and 104.27%. Now, some of you will look at this and say, but the student cannot get more than 100%. What if there was a bonus system? But anyway, if there's no bonus system, we could truncate the upper limit and simply say that it's between 80 and 100%. So that's fine. But if we just want to be technical and put down the answer that we got, then that's what we need to put down. All right? So remember that that's a confidence interval for the average value. So the average would be somewhere between 80 and 104 in that range. Now let's find a prediction interval for the same number of hours of study. In other words, predict what my mark would be. Now remember that this isn't the interval we just found was for the average. The average can be estimated with a much tighter interval. But then for actual values, the values have a lot more spread, in which case we need a larger interval, and it would look like this. So find a 95% prediction interval for the actual mark of a student who studied for 25 hours. Okay, so find a prediction interval for the actual mark of a student who studied for 25 hours. So the formula, we already know that 92.45 is our point estimate, plus or minus our critical value, 2.306, our standard deviation of the errors, 10.71, and then we have now 1 plus 1 over 10 plus 25 minus 18.8 squared over 297.6. And in that case, we got the following: 92.45 plus or minus, and the margin of error is much bigger in this case because of the 1, 27.38, which gives us that the actual value of y when x is equal to 25 lies somewhere between 65.07% and 119.83%. 119.83%. So in case you wonder why this interval is so much wider, it's so much wider because I'm predicting an actual value. Right? So let me just kind of illustrate what I mean. Let's say I had the following values: 2, 4, 6, 8, 10, 12, 14, 1, 2, 3, 4, 5, 6, 7. All right? So if I actually took the average of those values, I think the average would actually be 8. All right? The average would be 8. Now, if I wanted to predict that average, I could have an interval that's probably somewhere between maybe here and here. All right? That could be the width of my interval because I'm predicting the average value of y. But then if I want to predict an actual value, I have to consider the fact that the values could be all the way down to 2 and all the way up to 14. So clearly in that case, I would have a much larger interval when I'm trying to predict the actual value of y at a given x. Okay? So the actual value, because the values have a much larger range, would need a bigger confidence interval. But if I'm just trying to estimate this value in the middle, I don't need as huge a confidence interval. And so that's why the two intervals are different in terms of how wide they are. All right. So just to kind of sum things up, that brings us to the end of what we want to cover when it comes to regression. We are looking at what we call prediction and interval estimation. So prediction just allows us to substitute values in the equation. One of the things to keep in mind is that for the predictions to be valid, you can only use values for the x that are within the range of x values that you use to create the regression line. In other words, if we have when we fit the line, all of our points, let's say our points were in this range right here. So when we fit that regression line, if that was the range of the x values, let's call it x1 and x2, if that was the range of the x values that we used, then to predict a y value using an x that's somewhere out here, x3, is actually not legit, because you're trying to now project the line beyond this point. But the line technically is only valid for the x values, the range of x values that you use. So if your x value is within that range from x1 to x2, then you could go ahead and use that prediction, all right? But then if we are out here, then we are making an assumption. What's that assumption? We are assuming that this part of the line, that the line is actually going to continue exactly as it is, but we don't know. That's an assumption. So hence we have to be careful that we don't try to predict too far outside of the range of x values that we used. Okay? So on that note, just to recap, we started off looking at the relationship, the linear relationship between two variables. One is dependent and one is independent. So those two variables, we could measure the strength of the linear relationship with the correlation coefficient. We could also fit a least squares regression line, and that least squares line is one that minimizes the sum of the squared errors. We could also get what we call a coefficient of determination. That coefficient of determination tells us the percentage of the variation in the values of y that can be explained by the regression line. Then we went on to two hypothesis tests. The two hypothesis test allows us to look at whether or not x and y are linearly related. So that is a t-test for correlation. And we went through that. Then we could actually answer the question by doing the equivalent, by asking, does the x variable help to predict the y variable? And would only help to predict the y variable if the if the slope of the regression line is non-zero. If the slope is 0, it means that the x value has no influence on the y value. But if it does, the slope cannot be 0. Slope has to be non-zero. Finally, we said that we would like to be able to do predictions once we're satisfied that the regression line is okay. So with those predictions, we're able to get a confidence interval for the average value of y for a given x. So for example, students who study 25 hours, what's the average mark? And then we also could do a prediction, which is to find the actual mark of somebody who say, I studied for 25 hours. What is my mark? And then you could actually get a prediction interval. All right? So that wraps that up. The last thing that we want to do, I'll do it in one more video, is called ANOVA in regression. So we do what we call a goodness of fit test. We're testing whether or not the regression line that we got is a good fit. And there is analysis of variance in regression, believe it or not. Okay? Good. See you in video number 4.